Okay, Assalamualaikum. So we are going to continue with our lecture. Okay, so I left at granularity, concurrency, and task interaction. Okay, 3 out of 4 supposedly saya supposedly finish this slide ni dulu kan, slide ni dengan slide seterusnya. Tapi actually the first video tu was like a trial video, and then saya fikir biar je lah, bagi jugalah. So this is supposed to be a more proper video lah. Okay. So insyaAllah saya akan try bagi semua faham untuk CSC580 ni. Susah tak jumpa korang, dah lama dah rasa macam boringnya kalau tak boleh interact, boleh and so on. Yang ni tak apalah, kita buat yang mana kita mampu. Alright, so other than limited granularity and degree of concurrency, there is another important practical factor that limits our ability to obtain unbounded speed up. Okay, speed up ni basically dia antara ratio between parallel and serial execution time. Macam contohnya, okay, we have 160 second to complete this program. So this program sequentially takes 160 second. Kalau kita pakai parallel, contoh dia boleh kurangkan time dia in 90 seconds, for example. So what is the speed up of the program, of the parallel program? So simply bahagi serial bahagi dengan the parallel time. 160 bahagi dengan 90. Berapa 160 bahagi dengan 90? Calculator pangang kan. Okay, 160 bahagi dengan 90. Okay, meaning it performs 100 pula dah 1.7 times faster, 1.7 kali ganda lagi laju daripada serial execution. That is basically speed up. Okay, other than granularity, speed up ni satu lagi important factor adalah interaction. Okay, the factor is the interaction among tasks running on different physical processor. The task that the program is decomposed into often share input, output and intermediate data. Kalau they share input, kalau they share output and they share intermediate data, meaning apa? Every task has interaction between them. Maksudnya in order for them to obtain data, okay, process A nak data from process B, what does it need to do? It has to interact with process B. So interaction ni plays a very crucial role in speed up punya ratio ni. Okay, bukan setakat granularity dengan degree of concurrency je, interaction pun plays a vital role. For example, in decomposition for matrix vector multiplication, although all tasks are independent, they all need to access the entire input of vector B, meaning they are the shared input. Since originally there is only one copy of vector B, tasks may have to send and receive message for all of them to access the entire vector in the distributed memory paradigm. Kalau dalam distributed memory, dia tak share memory. So meaning setiap satu variable yang vector B tu, setiap satu proses kena simpan satu vector B. Yang ni yang kita kata macam walaupun dia actually share, tapi untuk kita tak nak ada interaction between them, kita letak terus setiap satu tu dalam satu proses. The pattern of interaction among tasks is capture what is known by task interaction graph. Okay, macam mana task interaction graph ni? Okay, yang ni jangan confuse. Ini basically very simple, tak ada benda lah. Memang kalau tak boleh jawab ni memang nak kena. Okay, for example, task 0 kat sini. Okay, kita tengok sini task 0. Okay, task 0 Task 0 dia interact dengan task mana? Kita tengok dia interact dengan task 1, okay, and task 4 and task 8. So dekat matrix ni, macam mana nak buat kat matrix ni? Task 0 dia akan interact dengan, of course, diri dia sendiri. Yang ni interact with itself lah. Dia dengan diri dia, memanglah dia kena interact. Okay, and then kita nampak dia 1, okay, and then 4, and then 8. Basically yang tu cara dia. Kita boleh translate, kita buat yang ni dulu ataupun kita buat yang ini dulu. Kadang-kadang soalan dia akan bagi yang ni, okay, it will give this and it wants you to answer with this answer. Sometimes it will give you this and then it will want you to answer in this manner. Okay, dia macam-macam cara untuk dia nak buat soalan. Okay, so untuk soalan final nanti maybe adalah benda-benda ni. Okay, final kita nanti final assessment, bukan final year, bukan final year pula dah, bukan final exam. Okay, final assessment macam we have to complete this assessment within 3 hours apa semua, dia ada macam tu, instead of kita buat final exam. So dia different sikit. Alright, So, okay, kalau tak faham lagi contoh tadi, kita tengok contoh yang kedua pula. Okay, satu ni interact dengan banyak task. Kita tengok interact dengan 0, interact dengan 5, interact dengan 2, interact dengan 6, interact, itu je lah. Okay, so kita tengok task 1. Task 1 interact dengan 0, yes, sebab tu dia ada kat sini. And then dia interact dengan diri dia sendiri, yes, so ada kat sini. Interact dengan 2, yes, so ada kat sini. Interact dengan 3, nope, no interaction with 3, has to go to true until it can reach 3. Then ada tak interact dengan 4? No, so tak ada kat sini. Then interact dengan 5? Yes, there are interaction with task 5. And then 6, ada 6? Yes, there is interaction with task 6. So yang ni je cara untuk buat apa, untuk sparse metric vector ni. Ini cara kita nak tunjuk dia punya graph interaction. Okay, yang ni dia punya matrices of task interaction, yang ni dia punya graph of task interaction. Okay, kita tengok processes and mapping lah. The tasks into which a problem decompose run on physical processes. Apa benda yang kita dah bahagi tadi tu, it will run in physical processes, not just decompose saja and then let it be like that. Tak ada. Once kita decompose, we will send the task into different multiple processes. Process in this chapter refers to processing or computing agent that perform tasks. Okay, during this time, in addition to performing computations, a process may synchronize or communicate with others processes if needed. Ini granted, macam kita buat meeting contoh dia kan. Kita dah semua, okay, each of us dah buat kerja masing-masing. Once each of us has done our work and so on, we have to sit down together and synchronize, okay, which have been done, which have not been done, macam tu. So there will be interactions among all those tasks. In order to obtain and speed up over sequential implementation, a parallel program must have several processes active simultaneously working on different tasks. The mechanism which tasks are assigned to process execution is called mapping. Maksudnya kita assign task to which process, that is called mapping, not just decompose. Decompose is one part. Once we have decomposed the task, we have to map the task into different process. So task A will be executed on process 1, for example. That is salah satu contoh lah. The task dependency and task interaction graph are result of the choice decomposition play an important role of the selection of good mapping and parallel algorithm. Kalau kita map, okay, for example, we have 3 tasks mapped into single process, and then another 5 tasks mapped into single process, and then there are ada 5 process left idle. That is not a good mapping. Maksudnya kita bagi dia ni banyak kerja, dia bagi ni banyak kerja, last sekali ada 5 lagi proses ni tak buat kerja apa-apa. That is not a very good mapping technique. Okay, kena buat mapping so that the task will be balanced and so on. Okay, kita tengok process and mapping. Keys to good mapping techniques. Maximize the use of concurrency by mapping independent tasks onto different processes. Kita kena maximize dia punya concurrency. Yang ni kita tengok degree of concurrency in the previous lecture dulu. Minimize the total completion time by ensuring that processes are available to execute on tasks on the critical path as soon as such tasks become executable. Maksudnya once task tu available je, maksudnya dia dah produce, macam kita perlu intermediate data kan. Siap je intermediate data, ada dah proses yang akan proses dia. Proses tu tak busy untuk buat task lain. Proses tu dah ready untuk accept the task. Minimize interaction among processes by mapping tasks with high degree of mutual interaction onto the same process. Yang ni another one. Okay, kita nak map process into high degree of mutual interaction and minimize interaction. For example, macam ni lah. Kalau kita buat meeting kan, asyik buat meeting, tapi kerja tak jalan. So what's the point of doing meeting? Of course lah kena buat kerja dulu apa semua. Once dah buat kerja, okay, we will conduct meeting, okay, next week. Okay, once everybody has done the job, and then we have meeting. Bukannya tiba-tiba okay, tomorrow meeting, okay, tomorrow meeting lagi, makan kari pak, okay, tomorrow meeting lagi, last kali kerja tak siap. So minimize interaction tu, instead of kita nak sentiasa interact with one another. Okay, do job and then interact. Okay, kita tengok next. Mapping techniques task based on yang tadi tu. Okay, for example yang ni task 1, task 2, task 3 and task 4. Task 1 kita akan bagi dekat proses 0. Okay, and then task 2 kita akan bagi dekat proses 1. Okay, task 2 proses 2, and then task 4 proses 3. Okay, basically kita dah map lah yang ni. Okay, we map into different processes. And then once we have this, okay, once kita dah ni, for example, P0 and P1 untuk task 5 ni, siapa yang akan pegang dia punya result? Contoh dia, kalau 0 dengan 1, of course lah between 0 and 1. Kalau macam ni kita letak P0. Of course tak ada masalah untuk awak letak P1. Jangan letak P2. Kenapa? P2 has nothing to do with task 5. Okay? P2 kat mana? P2 dengan P3 dekat task yang ini, task 6 ni. Okay, baru boleh letak P2 or P3. Nampak? Ini once dah habis dia akan bagi dekat P2. Okay? Then once nak kumpul result, P0 yang akan buat, ataupun kat sini in this case 0 or 2 boleh bagi dekat proses 2 pun boleh buat, tak ada masalah, as long as the task is related. Jangan bagi tiba-tiba task kat sini ada task 1, task 2, task 3, task 4. Okay, P0, P1, P2, P3. Dekat sini awak letak P5. P5 tak wujud kat situ. Okay, tak ada kena-mengena. Mesti letak proses yang ada kena-mengena. Macam kat bawah ni, between P0 and P2. So you can choose either P0 or P2 to get the final result. Alright. Cuba tengok A dengan B. Between A dengan B, dia punya concurrency lain. Betul tak? Alright. So cara mapping pun akan jadi lain juga. So cuba tengok kat sini P0, P1. So akan simpan kat P0. Okay, then P0, P2 akan simpan P0, P3 dengan P0 akan simpan dekat P0. Yang ni dia concurrency dia rendah sikit. Tapi cara dia mapping pun lebih kurang macam proses A pula, mapping A. So mapping A, mapping B lain, tapi degree of concurrency dia different. Alright, next. In the context of parallel algorithm design, processes are logical computing agents that perform tasks. Processors are the hardware units that physically perform computation. Processor ni apa yang tengah perform calculations. So in most cases we refer the processors in the context of parallel algorithm. Mau panjang pula benda ni. There is one-to-one correspondence between processors and processor, and it is appropriate to assume that there are many processors as the number of physical CPU on the parallel computer. Yang ni macam mana nak olah dia? It is appropriate to assume that there are as many processors as the number of physical CPU. Maksudnya number of process tu dia ikut dia punya physical CPU punya dia punya physical hardware dia. Contoh dia, kita ada 8 core. 8 core selalunya akan constitute berapa proses? Kalau 8 core 16 threads, meaning we will have 16 different processes. Macam tu dia tie with kita punya komputer kita. However, sometimes a higher level of abstraction may require to express parallel algorithms, especially in the complex algorithm and multiple stages of different forms of parallelism. Kalau ada different form of parallelism, complex algorithm, yang tu lain cerita lah. Kena buat lagi lah dia punya ni. Okay, so decomposition technique ada 5 different decomposition techniques. Okay, the first one is recursive decomposition, and the second one is data decomposition. The third one is exploratory decomposition, and the final one, the fourth one is speculative decomposition. Why the final one, the fifth one are not stated in the slide? It's not stated in the slide. Why? Sebab the fifth one is basically hybrid decomposition, meaning we can combine either recursive or data, or exploratory or data, or speculative or recursive decomposition, for example. Okay, combine dia akan jadi satu lagi, the fifth decomposition technique, which is called the hybrid decomposition. Okay, the next. Recursive decomposition is a method for inducing concurrency in a problem that can be solved using the divide and conquer strategy. Untuk recursive decomposition, kita pakai divide and conquer. So this semester you learn algorithm. So algorithm pun akan ada pasal divide and conquer. So yang ni dia macam clash sikit dengan syllabus algorithm. Bukan clash lah, syllabus yang sama. Okay, for example kita tengok quicksort. Here quicksort kita tengok. So we have this number. So macam mana nak perform quicksort? Kita akan select the first one as the pivot. Okay, we call this pivot. Okay, so buat turun dari 5. So anything less than 5 will go on the left hand side. Anything larger than 5 will go on the right hand side. So pecahkan dia. So mana kecil pada 5 belah kiri, mana besar pada 5 belah kanan. And then kita pilih pivot lagi. Okay, pivot dia 2 pula. So buat turun 2. Okay, and then pivot dia 8 pula, buat turun 8. Mana kecil pada 2 belah kiri, mana besar pada 2 letak kanan. Sampailah kita akan dapat apa? Kita akan dapat satu number. So we try to get back all this number all together. 1, 2, 3, 4, 5, 7, 8, 9. So the number are sorted. Yang tu Salah satu contoh recursive decomposition. Why kita kata dia recursive decomposition? Okay, kita tengok ini ya. Untuk serial, kalau sequential, kalau kita nak finding the minimum in an array, kita buat macam ni. Okay, kalau recursive decomposition, cuba tengok. Dia akan bahagi dengan 2. We call this divide and conquer. Sama lah macam yang ni. Kita akan bahagi 2, bahagi 2, bahagi 2 sampailah kita akan dapat jawapan dia. Okay, this is another example. Okay, padam sekejap. Tadi padam. Biarlah dia. Okay, for example, this another one. Okay, for example, kita nak cari minimum between 4, 9, 1, 7, 8, 11, 2, 12, 4, 9. Okay, kita akan buat pair lah 4, 9, 1, 7, 8, 11 dengan 2, 12. So, find dia punya mean. So, between 4 and 9 mana lagi kecil? Soalan bodoh. So, 4 di atas. Between 1 and 7, which one is smaller? 1 di atas. Okay, between 8 and 11, which one smaller? 8. Between 2 and 12, which one is smaller? 2. Okay, then naik atas lagi. 4, 1, mana lagi kecil? 1, so naik atas 1. 8 tu mana lagi kecil? 2, so 2 naik atas. Last kali kita akan dapat mean between 1 and 2 dan jawapannya akan jadi 1. Okay, it is that simple. Yang ni recursive decomposition kita akan bagi. Kita punya satu problem besar, kita akan bagi 2 sampailah kita akan dapat dia punya jawapan. The next one is data decomposition. So data decomposition is a powerful and commonly used method for deriving concurrency in algorithm that operates on large data structure. Kalau kita cakap pasal parallel ni, selalunya akan ada pasal big data. Macam data yang besar, kita nak proses dia. Okay, so bila ada banyak data ni sangat-sangat besar, apa yang kita boleh buat kalau kita nak buat parallel? We divide that data, we decompose that data, we call that data decomposition. For example macam ni. Okay, so kita ada matrix ni. So result will be, kalau kita nak darab, okay, kita nak multiply matrices macam matrix A dan matrix B, jawapannya kita akan ada C11, C12, C21 dengan C22. So how can we decompose this? Okay, kita pakai output data. Kalau kita pakai output data, so ada berapa banyak kat sini? Ada 4 different data. So pecah ikut. Task 1 will go to the will perform the first output data. Task 2 will calculate the second output data. Task 3 the third, and task 4 the fourth. Yeah, simple. Alright, next. Okay, this is two way of decomposing the output data untuk yang case study ni. Okay, yang ni yang satu cara, yang ni lagi satu cara. As long as you are very familiar with matrix multiplication and so on, there will be no problem for you for this. Okay, another one is we call this transaction. Okay, transaction ni macam database transaction lah, and then kita nak tengok dia punya item set or pattern dia. For example macam ni. Okay, we have all this database transaction and then we have this item set. So for example, kita nak kira item set ABC. Okay, item set ABC ni how many times dah dia buat transaction. So ABC, mana ABC? Kita dapat sini AB dengan C. So AB dengan C ada lagi tak? Tak ada. So kita kata yang ni adalah 1. Dan kita tengok DE. DE ada berapa kali? DE. Okay, yang ni first DE. Dan kita tengok DE lagi, mana DE. Yes, ni DE. Ada lagi tak? DE. So yang ni kita kata dia, frekuensi dia adalah 3. Nampak? Alright, so it's simple. Macam tak ada benda sangat. Benda ni very simple. Okay, so macam mana kalau kita nak partition dia punya output data? Yang ni dia punya output data, betul tak? So macam mana nak buat? Kita pecahkan dia jadi 1 dengan jadi 2. Okay, yang ni pecah dekat tengah ni, so dia akan jadi macam ni. Okay, it's very simple. And then kalau nak buat input data, macam mana pula nak buat input data? Input data yang atas ni tadi, instead of macam ni 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, pecahkan dia macam ni. Contoh dia. Okay, pecahkan input data, so akan jadi macam ni pula. Nampak? Right, so you can either decompose into input or output data. Okay, or you can also partitioning both output and input data to get more tasks. Macam ni kita boleh dapat 2 task, task 1, task 2, and then ni pun task 1, task 2. Yang ni boleh dapat task 1, task 2, task 3, and task 4 when we partitioning both output and input data. The result is still the same. Okay, once we combine all the result will remain the same. If the result is not the same, then there is an error in your algorithm So bila jawapan parallel tak sama dengan jawapan serial, that is a big problem. Okay, you have to make sure that jawapan serial sama dengan jawapan in parallel. Okay, next. Okay, yang ni kita panggil intermediate data. Intermediate data ni data yang dekat tengah-tengah, the intermediate. So for example, sebelum kita nak pecah matrices tu, kita boleh buat, instead of macam terus tambah, kita boleh darab dulu. Okay, for example macam ni. First kita akan cari dulu intermediate data D11, okay, D111, D112, D112 apa semua. Okay, kita pecahkan dulu, darab dulu, and last kali task 9, task 10, task 11, task 12 barulah kita akan selesaikan dengan tambahkan semua yang dekat atas ni. Mula darab dulu. Okay, macam yang atas ni dia terus tambah. Okay, instead of tambah dulu, kita darab dulu. Okay, times dulu, barulah kita darab dia. It is that simple. Okay, this one is intermediate data. So next is exploratory decomposition. So exploratory decomposition ni macam mana? Exploratory decomposition is used to decompose problem whose underlying computation correspond to search of a space for solution. Maksud dia dalam satu solution space tu besar. So macam mana kita nak buat? Instead of macam kita nak cari the whole thing, memang kita nak cari the whole thing apa semua. Explore ni macam kita ada 4 orang, okay, untuk cari benda tu. So 4 ni adakah perlu pergi tempat yang sama? Tak, dia akan pergi tempat yang lain-lain. So kita akan assign dia pergi ke A, yang ni akan pergi ke B, yang ni akan pergi ke C, dan ni akan pergi ke D, sampailah solution yang kita nak cari itu kita boleh jumpa. So for example, kita tengok 15 puzzle problem. Okay, 15 puzzle problem ni puzzle budak-budak ni. So contoh, satu cara kalau kita nak buat benda ni adalah kita boleh turunkan 3 ataupun 8 pergi ke kiri, ataupun 6 pergi ke kanan, ataupun 7 naik ke atas. Okay, tapi untuk dapatkan jawapan kita kena 7 naik atas, sebelah kita P, 12 naik atas, sampailah kita dapat susunan dia 1, 2, 3, 4, 5, 6, 7 sampai 15, sampai 15. Alright, but there are a lot of ways. Macam solution dia, kita tahu ni adalah solution dia, tapi ada banyak cara bergerak dia, kiri, kanan, atas, bawah boleh gerak. So nak buat macam mana? Okay, task 1 akan bergerak cara ni, task 2 akan bergerak cara ni, task 2 will move, task 3 will move another way, and then task 4 will move also another way. So we can have more variation toward our solution. So dalam task ni, task 1 akan tak dapat jawapan, task 2 tak dapat jawapan, task 3 tak dapat jawapan, last kali task 4 akan dapat jawapan. Nampak? Ni. Okay, so this is why we do exploratory decompositions, because we can have a higher number of success rather than just doing it alone. Okay, next. Okay, exploratory decomposition. In many instances of exploratory decomposition technique may change the amount of work done by parallel formulation. This change result in super or sublinear speed up. For example macam ni. So contoh dia, solution dia third trial baru kita akan jumpa. Ni kalau kita buat sequential, 1 tak jumpa, 2 tak jumpa, 3 tak jumpa, 3 baru kita jumpa, 1 tak jumpa, 2 tak jumpa, 3 baru jumpa. So task dia makan masa tak? Makan masa. Tapi kalau buat in parallel, macam mana? Masing-masing proses 1 buat, proses 2 buat, proses 3 buat, proses 4 pun akan buat. Pun terus dapat jawapan dekat proses 3. Proses 3 akan run sekali je. Maksud dia tak payah 1, 2, 3. Proses 3 akan run 1, 1 akan run 1, 2 akan run 1, 4 akan run 1. Tapi in one instances terus boleh dapat jawapan. Tapi it will be wasteful kalau macam ni. Contoh dia, proses 1 patutnya dah terus boleh dapat, tapi kita run yang the rest ni. Yang rest ni tak dapat jawapan pun, tapi dia kena berjalan juga. Yang tu dia punya sedikit waste kat situ. Sebab apa? Sebab sebenarnya kalau kita run sekali pun kita dah boleh dapat jawapan. Tak perlu run sampai 4 kali. Tapi yang untuk case yang depan ni, kena run 3 kali baru dapat. Tapi kalau run in parallel, 4 datang cari sekali, salah seorang dapat, habis itu. Right? So then speculative decomposition. Speculation. Okay, pernah dengar tak speculation? In some application, dependencies between tasks are not known a priori. Maksudnya dependency interaction A ni kita tak tahu dia akan interact dengan B ke, C akan interact dengan D ke. So for such application, it is impossible to identify independent tasks. Okay. So yang ni kita kena buat apa? Kita kena speculate dia punya decomposition. Alright, yang ni contoh a simple network for discrete event simulation, for example. Kita tak tahu dia akan pergi ke mana, so we can put in anything yang the possibilities of dia punya decomposition, kat mana yang dia akan pergi. Yang ni more towards the theory lah. Kita tak demo, kita tak simulate ni macam mana nak buat apa semua, sebab it is purely speculative and purely speculations. Alright, then finally hybrid decomposition. What is hybrid decomposition? Hybrid maksud dia campur. Okay, a mix for decomposing problem. Okay, consider the following example. In quicksort, recursive decomposition alone limits concurrency. Why? A mix of data recursive decomposition is more desirable. So apa dia boleh buat kat atas, dia mula-mula dia buat data decomposition dulu, and then di below dia boleh buat recursive decomposition. So mix up between different decomposition techniques, and then you have hybrid decompositions. Alright. Okay, characteristic of task interaction, yang tu will be the next lecture lah. Okay, kita akan buat 3 minggu lah untuk chapter 2 ni. Okay. Alright, with that I will end my lecture with this. Okay, thank you very much, and Assalamualaikum.